So we're supposed to use the ratio test to determine whether this series converges or diverges. Let me see if I can move the screen. That's great. Can't. Okay. I can do this. There we go. So to determine whether this converges using the ratio test, then we evaluate the limit as n goes to infinity for the absolute value of the n plus 1th term divided by the nth term. So I'm going to leave off the limit notation to spare my hand here. It's a lot of writing. We're going to just keep in mind we're evaluating the limit as n goes to infinity. So here is the n plus 1 term. I'm going to put this in parentheses, in a bracket too, because it's all being raised to the 4th power, right? We got to put n plus 1 everywhere where we see an n. So we got 4n plus 1 factorial and we're dividing that by the a sub n term. So that's just what we see up there, 2 to the 4n times n factorial to the 4th over 4n factorial. Okay, so we know that we got to flip and multiply. So let's also simplify this black side over here on the left of the division symbol. That's going to be 2 to the 4n plus 4, or in other words 2 to the 4n times 2 to the 4th. Okay, and then we multiply that by inside this factorial. I'm going to simplify a bit. N plus 1 factorial, that's the same as n plus 1 times n factorial. And the reason why I'm doing this ahead is because I know I'm going to have to somehow make it cancel out with some sort of n factorial term in the end, because I don't have an n plus 1 over here to cancel out. And I'm going to do the same thing on bottom. Look, this is 4n plus 4 when you distribute, right? So that's 4n plus 4 factorial. Or if you want to expand it, it's 4n plus 4 times 4n plus 3 times 4n plus 2 times 4n plus 1 times 4n, and then I'm going to stop there and put the factorial symbol back in, right? Because remember, factorial just means it's 6 times 5 times 4. It's all those numbers descending. So I just backed up until I got to 4n. That way I have something to cancel over here in red. So we rewrote the black part. Now let's flip and multiply the red part. That makes 4n factorial over 2 to the 4n times n factorial to the 4th. Let's see what we can do about canceling things out. We got to first winner of the day, 2 to the 4n and 2 to the 4n when we expanded this, right? Those are going to cancel. We also have 4n factorial, since we factored that out. And look, you can use the rule of exponents. Put this 4 to both these parentheses on the inside. And when you do that, n factorial to the 4th and n factorial to the 4th cancel out. So let's see what we got left over now that we have. I'll write it over here. Remember, this is all the limit as n goes to infinity. I just haven't written it so that my hand does not break. N plus 1 to the 4th over, we got 4n plus 1, 4n plus 4 in the denominator still, 4n plus 3, 4n plus 2, 4n plus 1 in the denominator. Okay, so we're trying to evaluate the limit as n goes to infinity for this expression. Remember, when you're trying to evaluate limits, think back to when we studied asymptotes, probably back in pre-calculus. What really mattered was the highest power in the numerator and the highest power in the denominator. And look, n plus 1 to the 4th, when you use your binomial expansion formula and you expand that, it's going to have n to the 4th. And down here, when you multiply these out, you're going to eventually have an n to the 4th. So the powers match. And when that happened with our asymptotes, like this this equation over here, the powers are the same. So the limit as x went to infinity here was 3 over 4. It was a ratio of the leading coefficients. So when the powers match, the limit as n goes to infinity is going to be a ratio of the leading coefficients. So let's just see what the leading coefficients are going to be in the bottom. 4 times 4 times 4 times 4. We're going to have 4 to the 4th, n to the 4th in the bottom. And in the top, when you expand this, it's just going to be n to the 4th times 2 to the 4th. So the limit as n goes to infinity, since the powers are the same, it's a ratio of the leading coefficients. And I think if you simplify that, that's 1 over 16. Okay? So we're finally ready to give our answer here. It converges because by the ratio test, since the limit as n goes to infinity is less than 1 but greater than 0, greater than or equal to 0, since the limit's between 0 and 1, it converges. I feel like I was going to say something else there, but that's all I got. That's it. It converges, right? If it was equal to 1, we'd say we cannot determine. And if it was greater than 1, if the limit as n goes to infinity was greater than 1, we would say it's divergent.